Okay, here we have with us Andy. So we're going to start with D-Wave. Andy is Sales Director of D-Wave System, and he's going to talk about D-Wave Advantage Performance Updates. So hi, Andy. Welcome to the workshop, to HPCQC workshop. And it's a pleasure to have you here, also this year. So I think you can start sharing.
Perfect. Thanks, Riccardo. Let me see if I can get some slides working. Okay.
Yep.
And I want to do a particular window, and I want to.
In the meantime, let me just tell the audience a quick thing. So there's gonna be in the chat a file where you can leave your name, enter name for those that are interested in having a certificate of attendance for this workshop. Okay, so people that are registered. Okay, so sorry, Andy, so you can
okay.
Go ahead.
Can you see my screen there?
Yes, yes.
Riccardo, perfect, good, super. Well, thanks very much indeed for inviting me. I'm very pleased to attend and be able to participate in this. Must be the fourth HPC quantum computing conference that you're running. So very big thanks to Daniele, Riccardo, and Enrico for organizing this. I must admit, I wasn't expecting such a rousing session from the professors Apolloni and Falco before starting this, particularly since it was such a lead in to a quantum annealing type approach. And it would have been fantastic if they, back in the 1980s, could actually have looked forward to today, where I'm actually going to talk about quantum annealing and actually hardware that can run quantum annealing problems. So that was very humbling, and I hope I can do them justice in the next 30 minutes with this presentation. So last year, when I was talking to everybody, we had just launched the D-Wave Advantage system, our new quantum processor unit with 5,000 qubits, and as our history shows, then shortly after launching a particular QPU, we then provide an update in terms of performance capabilities, and that's really the subject of today's conversation. I'm going to, for those people who are not that familiar with D-Wave, I'm going to start off just by giving a few introductions into what exactly the D-Wave system is, and then discuss what changes we've made. And there are a number of things we've done, both with the hardware and the software, which I will be talking about. And then obviously allow questions for anybody who has them towards the end. So no introduction of D-Wave is complete without letting everybody know that D-Wave is a full stack quantum computing company. We provide the hardware, we provide the software, and we provide services to go along with that to help our customers in developing the applications that they might be interested in. So we can do everything from start to finish, and the part of this you'll see is part of our cloud offering to provide those services out to our users. And I'm sure that a lot of you are using what we call the Leap developer accounts, whereby you can actually sign up for a free minute per month to gain advantage of the D-Wave services. I always go the wrong way. So this is kind of like our updated roadmap. Last year, it looked relatively similar. There were a couple of additions that I will point out today. But effectively, you can see that we've progressed and increased the number of qubits if we measure the hardware. And down at the bottom of this slope, if you can see my arrow, we kind of joined in this particular progression with our 2000 Q system with 2000 qubits. Prior to that, all of this history was not lost. And this is the part that got us from kind of the ground starting point through 8, 16, 32, 128 qubits to the point that we had 2000 qubits. We were then looking at speed ups, sort of theoretical speed ups on basically classical heuristics that were benchmark problems, nothing particularly real world orientated. So it was fantastic when we were able to show that on certain physics problems we were able to provide speed ups, and these were actually reported in Nature and Science magazines. Moving along this particular path, we introduced the 2000 Q low noise system. This system is still available. It has a slightly different fabrication to the Advantage system, and uses the original Chimera topology of having unit cells with 8 qubits in each unit cell. At this point, we were then able to demonstrate that we were actually using the D-Wave system on real applications. And then last year, we obviously introduced the Advantage system, as I described back in December 2020. And at the same time, almost overlapping, was the introduction of our cloud service and our hybrid solver services. I'll mention some of these again later in the presentation. But you can see here, this is where we are. And looking forward, the addition to this particular slide is the idea that we're now discussing what we're going to do in the next Advantage systems, Advantage Performance, that I'm going to talk about today, as well as Advantage 2 and Advantage 3. And for those who didn't perhaps attend our Qubits conference back in October, or have not been watching the news, one of probably the most exciting things for for everybody is the fact that we announced that we have started gate model quantum computing developments, and we now have a roadmap known as the Clarity roadmap that you can refer to on our website, that talks about how we are going to integrate gate model systems into our portfolio of quantum computing offerings. So we will be continuing with quantum annealing, as well as developing a quantum a gate model environment and architecture. And the goal is to have an overarching software suite within our tool set that enables us to look at a problem and decide which is the best architecture to run that problem on, or maybe parts of the problem, as you'll see with our hybrid solver services later on in the presentation. So from the hardware perspective, then these are some of the actual parameters, the features of our particular systems. So today we have 5,000 qubits. That's an increase from our 2,000 qubit system. And linking all of those qubits together, we have 35,000 couplers. This means that the degree, as we call it, which is the connectivity, has increased from 6 to 15 in the new Pegasus architecture of the D-Wave Advantage system. This means that each qubit is connected to 15 other qubits. So obviously the performance and the size of problems that we can address has increased from the 2000 Q system through to this Advantage. If we then look at sort of like a measurement in terms of how we look at classical computers, with classical computers, we're always talking about, or not always, but one measure of their size is how many transistors there are, or how the technology is advanced, is how many transistors there are in a particular surface area. Similar sort of thing for superconducting circuit fabrications, and this is looking at Josephson junctions. These are what effectively create our quantum effects and create the qubits. So here we're talking now in our Advantage systems of over 1 million Josephson junctions within our quantum processor unit. That's the hardware. As I said, within the lifetime of any D-Wave system, then we introduce both hardware and software improvements and additions as we go along in their lifetime. The one that we introduced at our Qubits meeting in October is called the Advantage Performance Update. And effectively, we have increased and improved our fabrication process in a variety of different ways. One of which enables us to account for more qubits. So if you do the maths and work out how many qubits there would be in our Pegasus architecture, then it's in the range of over 5,500. Some of these, when we actually calibrate the systems, we are unable to address. Each qubit needs to be identical, of course. So some of these we can't calibrate to be identical. So we then write them out of the graph. This means that we have to reduce the total number of qubits below the actual physical number. And so hence the name 5,000 rather than a higher number. In our manufacturing process that we've improved to produce the Advantage Performance Update, these new QPUs are actually higher quality in their fabrication, which means we can address more qubits. And by being able to do that, we're then able to look at larger problem sizes because obviously we have more qubits to address those problems. There's also within that hardware, we have enabled a lower energy technology so that we're not actually using so much energy within the problems, and we have more precision by looking at lower energy bounds within the solutions and the way we do the annealing. This higher quality answers faster part here it is an interesting fact. We obviously looked at these not all equal 3 SAT problems, and we actually ran those against certain heuristic samplers and looked at how they were getting on with regards to Advantage, as well as our 2000Q systems. And within the majority of cases, then the Advantage Performance Update was actually producing better, higher quality solutions than the other systems. Similarly, looking at 3D lattice problems, the same sort of thing was occurring, and we were getting two times faster solutions from the Advantage system. This system, for those of you who are using Leap, will find that this system is available in the cloud. It's been available since October, and I've often talked about the idea that a D-Wave system is being installed in the Jülich Supercomputer Center, and that is now fully installed, and we're going to be announcing that it will be available to everybody in January. So for that system, it already has one of these Advantage Performance chips or QPUs, has it installed. And so the minute we start in January, everybody will be able to access a European D-Wave node that is in Germany. So really looking forward to that being the case. So I mentioned the idea that we're going to be starting to look at gate model systems and develop that technology to supplement our annealing technology. So we often get asked this question: will the gate model development be replacing the quantum annealing and the D-Wave Advantage systems that are obviously a different technology? And if we see here, this is really giving you our view on what the future holds in terms of what sort of solutions, what sort of hardware is required for problems that are being faced by people in the real world. And this particular outlook shows that obviously it's easier to see the colors up here in the long term because the numbers are bigger. So if the dark blue is annealing, The turquoise color is problems that can be solved by both annealing and gate model, and the orange represents the sort of problems, the chemistry problems that only can be material science type things that can be addressed by best addressed by gate model systems. So if we look down here, then this is kind of today's analysis, and we can see that the actual division, the split, the quantity of these sort of areas doesn't really change much as we move forward. So there is still a space, primarily in optimization problems, combinatorial optimization problems, that will be best addressed by annealing solutions. So we will continue this annealing line at the same time as developing the gate model environment. And obviously a primary motivation to doing that is the fact that that means we will be able to address all of this marketplace here, rather than just a third of it as it looks in the long term. So our future is certainly still going to be fueled by annealing technologies, and we will obviously use the experience that we've had in developing quantum annealing systems in developing gate model systems as well, and look at how to get the best out of both systems to provide the best hybrid environment, including classical systems. So effectively, just to highlight the idea of how powerful optimization problems are and how powerful annealing is within this particular environment. So obviously there's some marketing sentences here, but effectively the important part of what I'm describing is on the right here, where I'm noting a couple of evaluations and problems that have been looked at by a variety of people, and we can see the fact that today the quantum annealing solution is actually providing much better statistics, much better performance than its gate model equivalent, whether that's QAOA or actual gate model itself. So whichever one we look at here, there are VW are being able to have solutions with a much larger number of cars involved in their paint shop scheduling. Ulick themselves have determined that the D-Wave system outperforms current gate QAOA. And this is a Los Alamos National Lab evaluation, which compares 15 seconds with the 30 hours. So some really good proof points about how well quantum annealing is performing compared with gate model solutions today on optimization problems. So that kind of wraps up the idea that D-Wave is producing the hardware in the Advantage system, and we've joined that together with the Leap Cloud. So being able to make improvements on both sides of this this particular slide in the hardware areas, which I've just described, and we're also making updates and changes within the software environment from our Leap Cloud service. We've talked about our hybrid solvers as a quick recap. Then prior to our latest announcement, we had two different quadratic model solvers, a binary one, which could address up to 1 million variables, and a discrete DQM solver, which can address a similar number of variables. And the premise here is the fact that a business application will have a flow, a hybrid environment itself, which might include areas that should have had that phone off. Include areas where we're going to be talking about classical environment, and this part here highlighted in the middle is where we're going to look at how that could be best applied to technologies that can address harder problems. And so we're within our hybrid environment, we're running this in parallel on classical optimization solvers and on D-Wave quantum ones. and effectively producing a solution which is a hybrid combination of these, which is of a higher quality and higher speed, higher value solutions to the customer's solution. So though neither of those two address constraint type problems, and so with the launch of the D-Wave Advantage performance update, we also produced we've launched a new hybrid solver, the constrained quadratic model, CQM, that effectively it makes it easier to address constraint orientated problems, as well as being able to overcome some of the problems that are normally associated with these types of problems. So we now have 3 hybrid solvers, DQM, BQM, and this CQM. And the whole process of using them is greatly simplified. A user effectively inputs the constraints of the problem into their Python program, and effectively it addresses some of the problems that we can't normally overcome very easily in these types of problems. So with the CQM, we're able to address integer variables, which we haven't been able to do so far. We're able to look at linear and quadratic terms, and within the CQM, we can address up to 1,000 constraints. And again, one of the important parts here is the fact that instead of looking at penalty functions for our constraints, we can actually input inequality and equality constraints as normal parameters, which then don't affect our solution in the same way that they might otherwise be affected. So a very much cleaner and easier solution. And if we look at using the CQM, then the CQM is in the turquoise color on the right. This is compared to the other solvers. And this is when we're looking at a Cubo problem. And this is showing how the performance can be changed. So obviously, in this sense, for Cubos, the BQM is performing slightly better, but not much than the CQM. But in constrained models, then we see how powerful the CQM is in being able to provide higher quality solutions than the other two solvers. So depending upon your solver, then it really depends which is the best choice. And evidently, for constrained quadratic models, this is the best solution. All of these solvers are available on the Leap platform, and they will all be available on the Ulix system when that comes into operation. Lastly, looking at the actual performance of these systems, then I think I've probably showed this slide before, but effectively this is the sort of how we're looking at problems in a non-quantum system, and then when we actually address them using the hybrid solver service, we get much better performance in a lot of the benchmark tests that we've done. Fabulous. And with that, I will end my presentation and ask if there are any questions that need addressing.
Thank you, Andy, for your presentation, for all the amazing updates from the D-Wave side. I think that participant, let me recall that participant can either raise their hands or write questions in the chat. So let's wait. So don't be shy and just raise.
It's early in the day, so we've got to get everybody's enthusiasms going. I think over the years, I've, for one reason or another, been one of the first presenters every time, and normally I have in early years there's been a sea of faces who are all, you can tell that they really want to ask a question but are worried they might be the first, so don't be shy.
Let me see if some of the participants. Okay, otherwise, okay, let me ask quick question. So more technical question. So how is it hard to build a device that is natively a DQM, so it solves natively something that is discrete instead of binary? So is it much harder, or do you know something in this regard?
So I don't know whether Victoria is available to answer that question, because she would give a much better answer. From my simplistic view, then I see it in terms of the binary. The BQM is very much the sort of the native version. That's what the machine was designed to address. And so it's kind of like a software layer on top of that to actually be able to cope with the discrete variables. But maybe that's too simplistic. Victoria, are you around?
Okay, let's see if Victoria is here, and if yes, we can. Yeah.
Hi, I am here. Yes. Sorry, can you just repeat what the question was again?
So the question was basically, so is it really hard to build a device that is natively discrete solver, so not binary, not qubits, but like qubits with the possible levels?
Yeah, so in our hybrid solvers, we have different ways of handling the different types of variables. But yeah, basically what Andy said is correct. You know, for the hybrid solvers, there's always some component of your problem that will run on the quantum computer, and that's natively binary. So when you have these other variable types, there has to be some way of either converting them or handling them so that when you run these portions of your problem on the quantum computer, it has to get converted somehow into that binary form.
Okay, thank you. I see also one question in the chat, so which says, what could be the reason for the difference in performances for certain application on D-Wave versus gate model quantum computation?
So that's a very good question. I would suggest that there are two reasons really why the performance there are the differences in performance. One is scalability. So we can obviously with our systems, whether it's with the native 5,000 qubits or the actual hybrid solvers, we can address larger problem sizes than can be addressed on today's gate model systems. So that gives us an advantage, because you might have to run the gate model systems multiple times to get the answer, or do some other non-natural way of getting the solution. The other aspect is the fact that these are optimization problems. And so the way that the D-Wave has been designed to actually address optimization problems means that in the same way that gate model have particular sweet spots or areas where they will outperform other technologies, optimization is D-Wave's sweet spot, and that's why we can give the better solutions. Added to that, of course, is the fact there's a third one. It's a Monty Python sketch. I have two answers. No, I have three. So the third one is the fact that, of course, we are less susceptible to the noisy environments that are with quantum computing today, and are a major hurdle that gate model systems that need to get over.
Okay, thank you so much, Andy. Thank you for answering the question.
Perfect.
I think so. It was a pleasure to have you here, you and also Victoria. So thank you again, and let's go to the second speaker of the day.